You happy to Yeah.
Okay, so ladies and gentlemen, back up here. So, what are you noticing? So, I'm wanting a polynomial that meets these requirements. So, I need p sub 0 to be 5. So, what am I actually telling you by making that statement? Looking back here at my polynomial, this is a 5th degree polynomial here. I'm sorry, 4th degree, 5 terms is what I meant to say. So, what am I telling you when I say p sub 0 is 5?
So when you plug in 0, you should get 5, so have like plus a constant of 5.
So, what is 5 then?
Constant?
Yes, but of my labels there for my
function. Is that the one on the far left?
It is, because there is no x, right? So this must be here. So p of x must be 5 plus. And then this says when you take the derivative and you plug in 0, the answer is 7. And take the derivative and plug in 0. What's so unique about the 0 here that makes it easy to figure this out? Like, there's a reason I picked 0. Yeah.
Every single term except for 1 will end up being 0 if you put in 0.
Right, so in fact, every term that still has an x in it is going to be 0 still. So when p prime of 0 is 7, does that mean that we know a1?
Yeah.
Is it 7?
It's the last one.
So is it just this?
Yes.
Careful. Is that the answer? Because thinking of what Matt said, did I extend it too far? Did I make too big of a generalization? Monty says yes. Anyone else agree with him? Did I go too far here? Jackson agrees I went too far. Megan, do you see something wrong?
Yeah, so when you take like the second or the first derivative, you have 22 dx, so then the third would be 22 and be 11.
Yeah, so I'm going to get a 22, which means what? How would I fix it then? How would I fix it? Okay, so if I do that, so if I say over 2 over 3 over 4, does that work?
No, because it's over 4 factorial.
Oh, why is that? James just said something really important. Did you hear him?
Because it's been on your graph for the past years.
Hang on, up here. So it's not this, and James said that this should be over factorials, right? So you want me to say 2 factorial, 3 factorial, 4 factorial. You need to explain that to me. So why is it that it's not just dividing by the power, thinking the chain rule? That's really what Megan's first comment was, right, with the 22. Notice that it works here because 2 factorial is 2, but Bish, why do we need these other factorials?
You take the derivative, you have to use the power rule.
So when I take the first derivative, I'm going to bring down a 3 here. And then when I take the second derivative, I'm going to bring down a 2. And then, so the only way I'm going to get all of that to cancel out to come back to the 13 if there's a 3 factorial present here. Questions on what we're setting up here? All right, let's pause and step back and think about this problem in a very different way. It's very intentional what I'm doing here to you to think about the warm-up. Do you notice that for this original polynomial, that I only know information at one point? Let me say that again. For the original polynomial here that I end up writing, do you notice I have one point that I know on that function? It is the point 0.05. At that x value of 0 is the only other x value that I know anything about for that polynomial. I know its slope at 0 is 7. I know its concavity, right, and how that rate of change, other rate of change, and so on. I know everything here is about 0. and it lets me write a polynomial. I'm kind of defining a polynomial based upon one point and the derivatives at that point. Do you see that? That's super significant. It might not seem significant, but it's very, very significant. So here's what I'm going to say. We're talking today at something called a Taylor polynomial. Taylor polynomial. This is one of the biggest topics in Calc 2 that you need to understand for your BC exam. And notice what I'm saying here, that I'm going to construct, I'm going to create a function by knowing the behavior only at a single point. Just like that first problem, I knew the point 0, 5, and I knew the derivatives after that all at 0, and it can make then a function that has that requirement, or those conditions, maybe I should say. So a couple things about Taylor polynomials. We'll talk about a Taylor polynomial of order n is what we will say, order n. And what that means is that the degree is n. So in that last problem, that last term was x to the fourth, right? So we would say a fourth order, or order 4. Notice, though, that there are n plus 1 terms. There's a constant term, right? And I will say this, that some of the terms may be 0, though. Like when I make this, it's possible that maybe the derivative turns out being 0 and maybe some of the terms drop out. So ideally there would be n plus 1 terms, but some of them may be 0, so then there would be fewer terms. And just like what we were talking about with our power series before, do you notice that really we just have, that's that similar idea really just being extended today, right? We have powers of x that are increasing. And so we can find new Taylor series by substituting maybe, or multiplying, or doing something to it. And we're going to see some of that here. So, Taylor polynomials. I'm going to put a definition here on the screen, and I want you to see how this is related. You don't have to write it all down, but you probably want to write down this portion here and mark it as a Taylor series generated for f at x equals 0. So notice I'm saying Taylor series, right? So I'm just adding together a bunch of terms here. And so notice what we have. We have f of 0. We have the derivative at 0. We have the second derivative at 0 divided by 2 factorial x squared. Do you see that this is exactly the thing that we just started the lesson with today? Right, it's the next derivative evaluated at 0 divided by n factorial. Now, this is a notation, and Anna, you saw this with that first problem, that means the nth derivative. So when you would see something like this, we just don't keep putting all the little tick marks there, so that's the fourth derivative. So that notation would mean the nth derivative. So what we're going to do is we're going to be able to find a polynomial that corresponds to certain functions here using this. I'll show you what I mean by that here in a minute. If you look at this summation notation, again, just to pick it apart to be sure we're okay with this, do you notice the index here is k, which is why there's k's written here rather than the n's, but you could have had n's there and that would have been k. Do you notice that this is an infinite series? Right, dot, dot, dot. I'm saying it doesn't end. and everything here is being evaluated at 0. That's why we might say it this way. Sometimes we would say it's centered at 0. That's a phrase that we would use. Don't need to worry about that yet. So what if I want to find the Taylor polynomial for a certain function? Okay, so here's a function, sine of x. So the Taylor polynomial centered at 0 then would say so think of the pieces. So f of 0 plus f prime of 0 x. Now if you wanted to actually, if you wanted to keep this totally consistent, you could divide this by 1 factorial. Again, do you notice that's really the power of x here that is what I'm dividing by? And if you wanted to even keep it more consistent, you could say x to the 0 there. And we talked the other day that 0 factorial really is what number? 1. So do you see how this pattern then would just be extended? So then you'd say the second derivative. The second derivative evaluated at 0. X squared over 2 factorial. Why don't you write out the first 5 terms for me? Okay. So actually find it. So that means you have a value for 0, right? So that means you can find the derivative and plug in 0. You should know sines and cosines at 0. So take a minute to write out the first 5 for me. What's your next term? It is just x. So if you stopped right there, if you stopped at x, that would be of order 1 then, right? Because it's x to the first. If you stop with your first term of 0, that would be of order 0 because it's x to the 0 power. So think of the degree there. What about the next term? Amber said 0 again. Is that what you got?
Yes.
Yep, so that one doesn't change anything. If I say order 2, it's the same. It looks like the same y equals x, right? We only have x so far. So in some directions, it'll actually then say, write out the first 5 non-zero terms or something like that. So just look at the directions. So I said, when I first was doing it and saying the first 5, we were thinking that all of those were going to be numbers the way that, or non-zeros the way I'd written it, but many of them are zeros. In fact, how many zeros am I going to get for this Taylor polynomial that I'm making? Every other, yeah. So in fact, every which ones?
Every odd term.
All the odd ones?
So like first, third, fifth.
Oh, wait. So tell me the degrees, though. So which powers of x then will be still present? Odds are still present. Every even one will be 0. So pause for a minute. Pause for a minute and think about this with me. There's a reason I'm showing you a graph right now. Okay? Because look at what I'm writing. I'm saying the sine of x equals. Now, I shouldn't actually say equal unless I would do this. ... Okay? So what I'm saying is that the sine function, this curve that we're used to thinking about with the unit circle and what the period is and how it behaves, that definitely non-polynomial thing is equal to this infinite polynomial. So watch this with me. this is, I think, pretty cool when you see it. So let me go back here. So here's order 0. So our Taylor polynomial of order 0 is the line y equals 0. How good is that to estimate the sine function? If you wanted to estimate the sine function using that polynomial, good idea or bad idea?
Depends on where you're looking.
I like that answer. Depends on where I'm looking. It's a great polynomial to approximate the sine function, especially at what value?
0.
0 or any
multiple of pi.
Any multiple of pi would be fine. But especially at 0. But doesn't that make sense? Because aren't we centering this at 0? I'm basically saying, what's the point on the function? Isn't that what that first calculation is? What is the sine of 0? Well, they better agree there. So look what happens. So as I increase the order, I now have a line that does better at approximating the sine function, doesn't it? So basically this, you could use the line y equals x to approximate the sine of x as long as I don't stray very far from 0, right? We have this locally linear idea really here that we've seen before. So there's order 2, nothing happens, right? Because that term is still 0. So now I have a cubic. Right, so here's my next term, so it's going to be minus x cubed over 3 factorial. Hopefully that's what you got. Yes?
Yes.
So what's the next one, based on what we said, is still going to be 0, right? So nothing changes at 4, right? Are you watching this? There's 4. So the next term is going to be what? X to the 5th over 5 factorial. Is it going to be plus or is it going to be minus? That one is plus. See what it's doing? Pause again. All we are looking at is the point at 0 and every derivative at 0, aren't we? That's all we're looking at. Isn't it amazing? It's fitting the curve over here, and all I know is the slope over here, and then the slope of the slope, and then its slope, and so on. Melissa?
So what's the difference between like the order and the power of a function? 'Cause, like, didn't we used to just say like the power function because x squared is 2?
So the order is the degree of this polynomial.
So is there no difference?
There's no difference, yeah. It's just a language of what we would call it. 6, nothing happens. There's 7. There's 8, nothing. 9, 10.
Actually,
And then it becomes a sine function.
and on the
Well,
on
if you
those-
go for an infinite amount of time.
If we were looking at that interval from just like 0 to pi, would that be exactly 1-to-1 for every x and y value, or is it just really close? Then?
So is it perfect? If I stop right now at 33 terms, is the sine of 2 radians going to be the value for this function?
No.
What do you think? It's going to be very close, but it won't be it.
Yeah. Okay.
So it's actually, if you think about it, that next term is probably making some adjustment across the entire curve, right?
Yeah.
It's not probably just adding something on to the end. So in fact, it's going to get tighter and tighter the more terms that I keep adding everywhere. So
So if you do an infinite number of terms, then
Wait, so if you keep adding on the end, it's still gonna get closer?
everything gets better.
Okay.
Yeah, everything gets better.
What does it look like?
Yeah, let me try to zoom out here. I forget how to do that on this. I'm not as good with GeoGebra.
use the thing right thing.
100 terms.
No, like in the art, that one.
Oh, there we go. That looks easy.
Try putting negative exponents.
Yeah, just a couple iterations.
Negative factorials.
Do you see here that on this side? So if you notice, where's the curve going to be fitting the best? Near 0, right? We're centering this thing at 0. Like everything is branching out from 0 to make this. And then if I zoom out, it's just fun to watch it.
Whoa, the Swift. You broke it.
Yeah, it's actually showing me over here like all 100 or so terms that and then doing a calculation. So if I do this, if I say f of 1.5, let's say, so that would, the interpretation would be, well, put 1.5 into this function right here, right? And so I don't know what happened. What did I do wrong? Oh, it doesn't like that. Why doesn't it like that? Not what I told you to do.
Ooh. Just look at the graph.
It probably doesn't want to round or something.
It probably just wants to
Because
show
it
you
plugged
the
in the
graph.
other
Yeah, it just didn't give me the answer. Like it,
Well, if you
Once
have
you
it,
graph
have
it
set to be
and
exact.
find the y-intercept,
I don't know.
it'll give you the answer.
yeah, it's actually just substituting in, which is not what I wanted to do.
It's exactly what you told it to do, f of 1.5.
This is what happens when you don't use that. Ralph Thompson, you need to use the real geometry sketch, not Walmart.
I know.
Walmart
It's
brand.
a great value.
Oh,
Yeah, it's a great value version.
So here's the thing. Sketchpad doesn't do this piece well. So anyway, so here's the point. So if we wanted to take, let's reduce this down to just a couple terms here. Okay. So I'm going to get rid of this. So do this with me. Take a calculator.
Which one?
I don't care. So let's take this function and go ahead and evaluate both of these functions at, let's say, 1.5 and calculate the percent error for me. Since the...
Can you zoom in on those?
Sure.
Sorry, I think I'm losing my eyesight.
Is our factorial button on this?
Is that better? Oops.
Oh, it's frozen.
Oh, sorry.
No, I meant like on the actual formula.
Is there a factorial button on
Is that better?
That's better though, thank you.
We plug it into one, subtract from the value of sine, divide by the value of
Oh,
sine.
that's right.
You ruined me. 120.
Yes. If you want 100%.
Which one do you subtract to the percent error?
How do you do factorial?
It's usually considered absolute value, so it doesn't
It's
matter.
like original.
So, what is it, actual minus estimated over actual?
Actual minus.
Yeah, as long as you keep track of it, you'll know that the percent error, which one's bigger and
Just
smaller,
a button,
right?
but like, just do probably 4 to 3.
Yeah, just do catalog.
It's
I mean mode. No, not mode, catalog.
For factorial, I believe there is a hidden shortcut,
It's the diamond, it's the green key and then like one of the buttons.
like
One of
divide,
the
try
buttons.
divide,
3%.
Guys, I think
Yep,
it's-
it's
I think it's diamond,
alpha
diamond.
divide.
alpha divide.
Diamond divide?
No, you mean diamond, right?
Diamond?
Yeah, because alpha divide is.
Oh, not alpha, diamond, yeah.
It's
Because
diamond
I know,
divide.
there's no like, like diamond 7. Diamond 7 makes you log with any base skill.
Wait, really?
That's pretty good. That's.
Today we learned about the TI-89.
Yeah, diamond has all of the shortcuts.
Dude, diamond's a pretty big one.
Show me the key diamond. You know it's small, right?
Yeah, I know. Yeah, I know that one. Oh, the Goshi.
Wait, so it's just
Second
the
seven
three
or
turns?
for intervals of three?
Alpha 7?
You just wanna really like,
Oh, yeah.
Alpha.
when you just don't like seven, but you wanna actually open the menu.
Second.
Dude, there's an and button.
Oh yeah, use that all for semester.
It is
Like,
mine.
yeah, use that all for semester.
I don't know why we don't tell you that.
That's how you did
Wait,
it.
And
Ampersand?
do the
What do
equal,
I
like
need an
the
ampersand?
diamond and then equal.
What?
Diamond multiply sign.
Oh, yeah, it's and. You don't type in things. How do you like type
Wait,
inside
dark
your?
is this
There's a
vertical line
notebook.
absolute value are?
Yeah, I know, I made a note earlier.
Such that.
I'm gonna go to, you can just, I'm not sure why. I'm gonna go into.
Lets you actually evaluate like a derivative you would use that.
Yeah, it's something
Study cards.
He's gonna be like, going to work. I'm gonna be like, I'm taking.
A clock.
Would you like take me? Okay, this is easy.
My clock says
Yeah.
my clock says 1997.
Dude, diamond.
Boom! 336.
So, ladies and gentlemen, so I don't know. I typed the same thing in here, so it may not like the number of terms and just want to evaluate it when I had it way out there. So down here it does. I've got these two values.
Yeah.
So the bottom one is our Taylor polynomial. Now, even just looking at that, you can tell we're going to get a pretty small percent error here, right? What is it?
0.3%.
0.3%. So as the terms go up, let's see how long it keeps it.
It's 0.32945.
Hang on. Not sure why y'all talking. Up here. So look, here is the through order 5. There's 6, which doesn't change, right? 7. Look at this.
Why are they both chicken?
That's a good. No, they're not. It's just the bottom one, right?
Oh, okay. I thought they were
Yeah,
both changing.
that would be a problem.
Oh, no, it's just rounding.
Oh, that's cool.
And I can try to see if we can get it to show more digits here. But you can see at some point.
15 decimal places. 15 significant figures. 8 significant.
That's what it is.
That's why.
Look at how many decimal points agree there.
Not enough.
That's all lines.
That's all 15.
So here's something to think about. With thinking of the number of terms that are needed here, it's really not that many to actually then be able to think about a very accurate approximation for a sine curve. Again, as long as we don't stray from wherever it's centered. So what if I want it to be centered though at pi? What do you think would change about our Taylor polynomial? So I'm going to go back here, and so let's make it just simpler here for a minute. If I want this centered at pi, then that means I should have been finding the derivatives at, well, pi then, right? But graphically, how could I also understand that? So it wouldn't be this line. It would actually be this line where?
But then reflect it, right? You have to multiply
Isn't all the
-1.
positives and negatives gonna flip?
Yeah.
So it needs to,
Multiply -1, then move the
Just a Taylor polynomial function.
so it's going to go here. So that's what you just said, right? It's got to be kind of going the other direction because you're looking at pi. But do you notice that this should make a lot of sense?
Yeah.
Graphically, all I'm doing then is what? Yeah, I'm translating it, right? I'm moving it over. Now, why is there going to be a negative? So in fact, all the terms that I had before that were the ones that were positive, are they going to now be negative and vice versa? So We'll go to the next one. So, what was the cubic term before, positive or negative?
There's negative and now it's positive. There's a negative.
Okay, now the 5 is negative. Yeah, why is that happening? By the way, if you look at this graph, do you notice that now I'm building my polynomial coming out from pi? Right, do you see that? Like as I add these terms?
11 week school.
Think about the difference between 0 and pi. Somebody said it. Somebody mentioned something about cosine.
Cosine of pi is
Cosine of pi is -1.
0 is.
And 0 is 1, so with that, shouldn't there have been another negative involved in this problem then? So that's what's happening.
Wait, why are you talking about this?
So if it's centered somewhere else, so all of your calculations now, so if I go back here, think about what we wrote here. This then would be the polynomial centered at 0. If I want it centered at pi, I would have to do this. I would have to say the sine of x is f of pi plus f prime of pi, x to the first, plus f double prime of pi, x squared over 2 factorial. Do you see that pi is now the key to all of these calculations? And then so the sine of pi is still 0, so all of those terms still drop out. So all of these other ones are cosines, which are going to have a -1, which flips all the signs. Okay.
So it doesn't necessarily matter the x value that you may be centered at. That doesn't change anything as long as you have like infinite terms.
I'm sorry, I wrote something wrong here.
Yeah, x minus pi.
Yeah, sorry.
Okay, I was confused.
Sorry, James.
Disservice.
It doesn't matter, because so here's then what I'm saying, that if I would have an infinite number of terms, this polynomial is also going to equal the sine of x. Now, think about this for just a minute. And so in terms of programming, here's an important point. Once upon a time, if people wanted to know what the sine of any value was, and you didn't have a slide rule, you would look in a book. And you'd look up whatever, and somebody else had worked it out, and you get the value you want. So even thinking your calculator, if you ever pause to think about how does your calculator know the sine of 1.25 radians? It didn't look it up in a book. Couldn't, instead of the sine function, you just have a polynomial? Now, if you think about it, if I want a very accurate representation of sine, I actually have gone probably much further than I need here. Because this is a periodic function, isn't it? It repeats itself. If I can get something really accurate over a single period, then couldn't I translate that to any other period and get the answer that I want, thinking about that shape? So I don't know this for certain, but I would suspect that calculators, especially maybe older calculators, would have just had a polynomial. And it would have just written a program such that if somebody puts in an angle that's bigger than 0 to 2 pi, it converts it to 0 to 2 pi, and then it plugs it into the function and returns the value, because you can see how close they get with not all that many terms. It's very simple. It's very elegant, actually. And awesome.
Awesome, simple.
So basically, a sine can be thought of as an infinite polynomial, which means a cosine
Can also be thought of
can
as
also be.
Polynomial shifted horizontally.
So why don't you write out the first few terms here. Let's center it at 0. Okay, so what would the cosine of x be as a Taylor polynomial? you're going to have to build these, and this is a really common BC question. So where we're centered, f is 0, f prime is 0, x first, f double prime, etc. Difference though now is that f of 0 is not 0, f of 0 is actually 1. Plus, what happens here?
0.
That one's now 0. So in fact, do you see what's changed? Before, all of the odd ones were, well, they were there, and the even ones were gone, and now it's reversed, right? Now all of the odd ones are zeros. And is there also a plus-minus pattern that's going to happen with cosine?
Yes.
Because of derivatives.
Because of derivatives.
Cycle back and forth.
Magic.
Magic sounds a little sketchy.
Magic is always sketchy.
Oh, that's maybe true.
Yes, it's a lot less sketchy.
So here's our cosine. Here's the first few terms of a cosine. Look at yours, see if it matches, and we're going to do something else with it. So let me set it back here again. So notice that here's our first line, right? It's at the only point that we know. Next one, 0. There's a very nice parabola. It fits it. 4th degree. So, is there any function I couldn't write some Taylor polynomial for? I mean, as long as I could keep writing derivatives, couldn't I come up with a Taylor polynomial? Things like exponentials.
What would e to the x look like?
E to the x. Well, you tell me.
Just follow my order.
So I'll change it here, but
Or you can just write a power series for it. Don't worry about it. That seems a lot easier.
so there's e to the x. So centered at 0, so put in 1 to e. I'm sorry, put in 0 to e to the x to get 1, right? Which we see here. What's the next term going to be? Come on, what's the next term? It's a polynomial, right? So you've got to tell me powers of x. So it's got to be x to the first. What's the coefficient of x to the first? Close. It's not e to the x. Somebody else said it over there. It's
E
just
times x
e.
is the...
Yeah, that's what I think.
Why?
One plus x.
What's it doing? That's not right.
Uh-oh. You broke it.
Second.
Gotta use those.
Weird
Yeah, you gotta use that.
Geometry's gonna tell you you don't have.
All right, wait. So next one, I need to take the derivative. So it's e, but to what power? So it's e to the x. Then what? Are you with me?
It'd be
Go back here. This is all I'm saying. If we do this, and so the question was, what if it was e to the x? So what's f prime of 0?
e to this. It just be 1.
It's 1. It's e to the 0, which is 1. So it's going to end up being, so the first term is 1 plus 1 times x plus
1/2 x squared.
1/2 x squared. Do you see that this value is always going to be what?
1.
It's always 1. So its derivative is e to the x, but then you're going to be substituting in 0, so e to the 0. And that actually is what we saw the other day, isn't it? So here it is. It's working. This was the one that James, you said, oh wait, it's converging. Like there's, it's going to converge for all n at the time I think I had written. And that's actually what we're seeing here, that as long as I have the infinite number of terms. All right, something more interesting in the last couple minutes, but it's really hard to top this. But I don't want to disappoint Matt.
But we have this.
Guys, we're gonna write.
Are you ready?
No.
Brace yourself.
I'm braced.
Fire alarm goes off.
Are you there?
So let's start with this. So based upon what we just saw, e to the x, so let's write that out. Okay, so e to the x. So e to the x is equal to, is the same thing as, is equivalent to, as long as I have an infinite number of terms. So it's 1 plus x squared over 2 plus, what's the next one? Over 3 factorial. Yeah, you can leave it as 3 factorial, that's okay. All right, so this continues. So I'm not going to keep going there. So what do you think I would do here?
Give up.
Don't give up. It's not impossible. Come
It's
on.
not impossible.
Oh, you
but
put
it's
in
not
a line.
like thinking about it.
Wait.
What?
Think about,
Think about
I
it.
said at the beginning that we could make new ones by like substitution or working together. So really, if this is true, then shouldn't e to the ix be basically put an ix everywhere we see an x, right? Isn't that the substitution I'm making here?
Yes.
That means you now can write a polynomial that represents this. So do that. And yes, you have to remember what I squared is and I cubed and I fourth. There's
If I
pattern.
don't want to expand it.
Don't expand. Well, no, there's nothing really to expand. Okay, so if you've done that,
Oh my gosh.
there's going to be a bunch of terms that do not have I in them any longer, right?
Yeah, but there are also a bunch that still do.
There are. So what I want to do is I'm going to write it after here in a minute. I want you to take all the terms, you might need to write out a couple more, and I want you to factor the I out of the ones that still have the I's in it, and then all the other ones I want you to put over here. Okay? So every term that still has an I in it, factor it out and put the remaining bits here. The terms that don't have the I in it, put here. So like you're going to have 1 plus, this was I squared, which is -1, so it's going to be minus x squared over 2 factorial would be in this box. Over here, you're going to have 1 because you really had an I, so it's a 1x, taking the I out. And then you're going to have minus, you should have an x cubed over 3 factorial here. Decide what operation I should put in that box. That should be plus or minus.
It's a
It is going to be plus,
real,
yeah.
like, it's a complex number, right?
Yeah, we actually can think about this as a complex number, but we're not yet.
Yeah.
Something better is going to happen.
What's better than a complex
Oh,
number?
you have to hold on.
Is it a matrix? There's also one of those questions on the ICT.
You are close.
We're so close.
Now look at what you have carefully. Carefully.
Oh, I missed it.
All of this stuff in blue and all of this stuff in green, you have a better name for. You do. You just wrote it down. The stuff in blue.
Wait, is it the sign?
I don't know, look.
One is just the.
One is the derivative.
Oh my
That
god.
one.
Yeah.
Wait, what do you see?
Oh my god.
Green, blue is the derivative of green.
Oh, do we know a relationship such that that is true? So which one is sine?
Sine is
That one.
the green.
Yeah, and if you look at what you wrote down a minute ago, that isn't that the terms that we had for the sine?
Oh my lord.
No!
What's this?
Wait.
Oh wait, no, my deck.
What? What?
Okay, we're not done yet.
It's how you have sports vectors.
We're not done.
We're almost done.
Let's grab
All right, you ready? You ready? This is saying, remember that this was equal to this with my infinite number of terms, and now with my infinite number of terms, I can actually just represent them as these other trig functions, which means if I put a value of x in here and put the same value of x in here, these things are supposed to be equal, aren't they?
Yeah.
Right? That's what we're saying. So we can pick any x we want. Why can I pick any x? Well, if I'm thinking about an infinite number of terms, if I keep adding all those different derivatives on, like it keeps fitting, right? It is the function. So the x that I am most interested in right now is
7.
pi.
Oh.
So e
E to the I
to the I pi is equal to the cosine of pi plus I times the sine of pi.
So it's just I.
So what is the cosine of pi?
0.
Try again. It's -1. What is the sine of pi?
0.
Euler.
What?
So in one single equation, so here's one equation. That -1 is the same number as e to the I pi. And in this single statement, notice that we have our two favorite transcendental numbers. We have the complex imaginary unit. We have 1 and its opposite, and then we have 0, all linked together in a single statement.
Why?
So,
But what does this have to do with anything relevant to literally anything?
0 equals e to the I.
sometimes it's written this way. Let's see, I think 2 weeks ago at math team, John DeForest showed up for fun, and he was wearing a shirt that said, "This shirt has made me this many friends." But we understood, at least I did. So, but anyway, so this is a good place to end for the day. So
What's the practical application?
you're welcome to look that up. There actually are some thinking about this as a even in terms of electrical connection. So 10.2. Just another day.
Are we gonna be able to do
I thought you were joking when you said, let's do
Are we gonna